All right, we're now going to take a look at the next quality control block here in the AFNI HTML. This is the radcor block, which is the radial correlation or local correlation. And we're going to see that we actually have potentially several different images here. Each one is for an individual run and for an individual step processing block within the AFNI proc command. So we have run 1, run 2, and run 3 here. And we also have the label that tells us which processing block tcat. If we look at our AFNI proc command of our processing blocks, we'll see we don't actually see tcat. Tcat is what's called an implicit block. That is the very first block in processing. The other two blocks we'll look at here are vorig and regress, but essentially tcat, it's the copying in of the data. So absolutely no processing, just maybe truncating the first TRs of the data set if we ask for it. So here we see an option for tcat removing the first two TRs. So this will be the radial correlation of the initially copied in data with the first two TRs having been removed already. Okay, and so what is radial correlation? Radial correlation is going to every single voxel in the field of view, and we take the time series there and we correlate that with an average time series of a ball drawn around the center of that, drawn around that voxel. So it's a pretty large radius ball, and we're basically looking for what is the correlation of each time series with its larger neighborhood. What is the radius of the ball? I believe it's 20 millimeters. I can check that by looking at the @radial correlate help. And if we see here, it says the program computes a correlation at each voxel with a time series and a 20 millimeter radius ball by default. So we could set it, for example, if you're processing non-human data or something with a different size brain, that might make sense. But okay, there we go. So that's what we're looking at here. And as we see here, let me just scroll down a little bit. For the 3 runs here, we notice that we see some kind of similarities and differences. The similarity is all around the edge is where we see the brightest color, the most opaque. And what we'll notice here is that we're using the alpha transparency threshold again, thresholded at 0.4. So we're looking at correlation values everywhere, threshold at 0.4. And we have alpha transparency on, meaning that we see correlations everywhere in the brain. Things that are below 0.4 are fading away, so they're de-emphasized. We don't draw lines here because the underlay grid is the coarser EPI grid, and the lines would kind of be ugly and distracting. So we're just seeing the alpha transparency. And so wherever we see opaque things are where there's the largest value. And if we wanted to, we could click on the NV button, for example, and surf around and see what the value is at a particular location. Here, the overlay value is 0.46, fine. Or we could click the AV button and also see this in the AFNI view here. And again, we could surf around and see whatever value we wanted. It's 0.43 or whatever it is. Okay, so we can get that more detail if we need it, but this is really typically not necessary. Something that's so we said it's similar that there's the highest values around the edges, and actually we see here some ghostly edges outside the brain. Those are really where the skull is as well. Down here in the most inferior slices, we'll see some more things. This is typically maybe around the eyes, we might see more, or with ghosting, and often these higher values around the edges, both of the brain and of the kind of skull outlining it, are because there's a little bit of motion in almost all EPI scans, as well as some other effects. And actually in run 1 is where there's the most motion. So if I quickly hop back up to the moat QC block, we see that there's some motion in run 2. Again, these white, gray, white background tells us which run is where. The most motion and the most outliers we see are actually in run 1, and less in run 2, and almost nothing in run 3. And so we get a sense a little bit that this radial correlation, there's more local correlation, particularly around edges and where tissue boundaries are, correlation and anti-correlation, and it's often due to motion or other effects as well. In this case, probably mostly motion. And so that's okay. We know that there can be motion in our data, and we'll want to deal with it in our processing with censoring and with potentially regression and some other things like that. But this is just the initial picture here of how things are. All right, and if I scroll down to the next trio of images here, so this is in the vorig block. So this is after volume registration. And the way we've ordered our processing blocks here, this is even after a Taylor Act. So this is motion correction and in final space. We can see here now that this is the run 1 image of radial correlation and run 2 and run 3. And these actually look a lot more homogeneous. Run 1 no longer looks so much more intense with its coloration around the edges. And we have not done any regression yet. This is simply by doing the geometric corrections of motion EPI alignment. So resetting where a particular volume of motion is, aligning it to a reference volume, that alone helps reduce some of these spurious high correlations within neighborhoods. And this is pretty typical that we will see correlations. Often what we hope to see by the end of this is mostly in gray matter, not so much around the edges, and also not extending across different tissue classes in weird geometric structures, either across a slice or in a column or something like that, or weird patches that extend across. So this is looking pretty good and reasonable. And if we wanted to, we could always look at, I forgot to mention, there's now the IC and the GV buttons that are here. So let me scroll back up for a second. If I wanted to see for any of these runs something I could investigate with like Instacore or the graph viewer, just to see what those look like. So now in this case, the dialog pop-up tells me that what I'm looking at in my graph view. Earlier, we saw an example in the VStat section where we're looking at the ERTs or the residuals from modeling. We haven't gotten to the modeling point yet. We're simply looking at the copied EPI data set itself. So recall that this is telling us it's radcor in the TCAT block. This is just the TCAT data. This is the copied in data. So this would be a good juncture actually for using GraphView and maybe even Instacore to understand the data to see if there are some weird structures in here just from copying. And we don't need to overlay or anything. We can see here if I just go back and click kind of in gray matter, maybe in the visual cortex, I see that there are motion spikes here, and this is probably driving at least some of the correlation and anti-correlation patterns. If I go down here to the visual cortex, I can even see some of my block design structure here. So I can see both some of the positive and negative features of my time series, depending on the part of the brain I click in and the tissue and things like that. So this is one way that it can be useful if you want to see just the original TimeCat data time series. Then you can jump to the radcor block and click GV, and then if we wanted to run Instacore on this data, we could. I'm not going to here, but this is a way that you can see the time series from some different parts of the data during its processing. So this is something I actually do make use of for other reasons, and we'll come back to that. Okay, so we had gotten down actually to the vorig block. If I click GV or IC here, I will see the graph view. Maybe I'll do that now just quickly because I did up above. Let's look at what our time series look like. So the PB vorig data, so PB02 now, again, just for run 1. And if I click around and go somewhere toward maybe somewhere like the visual cortex, actually the spikes are a little de-emphasized now. The data has been both de-spiked and we've done this volume registration. And so now I see actually more just the block design response that I might expect. There are still spikes here up and down, and actually some of them can still be reasonably large depending as I click around. And again, they'll be almost randomly up or down depending on the tissue motion and things like that. But anyways, this is just to get a sense of how the data is propagating as it's being processed here step by step. So this can be useful. I don't see anything alarming here. This level of mostly kind of local positive correlation, mostly contained in gray matter, seems pretty good. And then the last section of this, or subsection of the radcor, is now in the regress block of processing. So after regression has taken place, now in this case, we don't have 3 different runs of data, because after regression, we've concatenated all our time series in the processing, so we just have our final run. And so if I click GV now, actually, this is going to be showing me, as up above, the graph time series of the ERTS dataset, the error time series, or the residuals from modeling. This looks very different than before, because I don't really see gray-white structure, because this data has been scaled, so it all has a constant mean value, and the bold fluctuations, which are only of order 1 to 2 to maybe 3%, those are very small fluctuations. So I just see a little bit of fluctuation of this kind of mostly gray, but I do see there are real fluctuations in the time series. It's just they're all small with respect to the mean. If I wanted to see where I was in terms of structure, I could click on overlay here. And something I should have mentioned above, I'm clicking overlay because the graph view is always of the underlay data set. So I want to leave that of the EPI. And I might just overlay the final anatomical data set if I wanted to just give me something that shows some structures. And this is good enough even without playing around with the color bar. I can tell where gray and white matter are and things like that. Okay, so I could look at the graph view here. Of course, my EPI field of view, as we see here, doesn't cover the whole brain. I can see in the background where that is in the final data set. But anyways, so I could look at the residual structure and see if there are weird structures maybe left in here that I might be worried about. Our data has been blurred as part of processing. Again, if I jump back to the AFNI proc command, we had the blur block before scaling and regress. So I might not be surprised to see more local correlation everywhere, this radial correlation, but I'm happy that it's mostly contained in the gray matter. When we apply it here, also we do apply the mask to the data set. So our data, as we saw in VStat, is not actually masked, but when we view it here, it is masked, so we're not correlating with structures outside the brain. That's the idea. But for other parts, we really look everywhere. All right, so this is a brief glance through this radcor block. Again, for the early processing blocks, when we look at things there, for let's say vorig or TCAT previously, we look at each run separately. For the regress block, it's just the ERTS data set because everything has been concatenated. We're using transparent thresholding, and we're mostly happy when we see kind of generally positive correlation, mostly in gray matter, and certainly not spanning with weird structures throughout the brain. Excuse me, I could also click on NiiVue here and just see if there are other structures, throughout the brain in some different geometry. I could click here and see for clipping, and I don't see any weird geometric structures, so that's all making me happy from this. We'll look at other examples later for different data sets that do have weird structures, unfortunately. All right, and we'll look at the next block in another video.